Closing out from physics, John Huth.
Let me light your candle, cause mama, I'm sure all the hand and just around. Yeah, all the hand now. Oh, baby.
Does this work? Can you hear me? Okay. So, and I can advance the slides here. Okay, cool. Okay, so my name's John Keith, and I'm from the physics department, and I guess I'm doing cleanup here. Physics in baseball is a huge topic, and I couldn't possibly even touch on all of that in a short amount of time. So what I'm going to talk about is this very magical moment between the time the ball leaves the pitcher's hand and when it crosses the plate, and just focus on that little bit, because there's a lot of interesting stuff that goes on, and it's actually rather complicated. And yet, as physicists, what we like to do is try to take something complicated and boil it down to a few small principles. And so the first question is, well, what goes through a pitcher's mind just before the delivery, okay? This, obviously maybe not this, but this is called the Navier-Stokes equation, and it describes the motion of an object through air or through a fluid like water. A baseball is basically going to obey these equations, and it looks ghastly. It looks ghastly to me, okay? If it looks ghastly to you, it even looks ghastly to me. Nobody has ever solved this. The Clay Institute of Mathematics is offering a $1 million prize for somebody that can show the existence of a solution to this. Not a solution, just the existence of a solution. So that's not going to be going through the player's mind, and in fact, what the pitcher will probably be doing is using muscle memory, having practice over and over and over again, seeing what effect the grip on the ball does, or how they move their arms on how the pitch gets delivered. So I'm going to talk a little bit about what is actually going on. Now, people knew that a spinning ball would actually curve one way or another for quite some time. In fact, Isaac Newton noticed this way back when he was in Cambridge looking at tennis matches. For some reason, it had been incorrectly attributed to physicists that we said that curveballs were an optical illusion. And in fact, there was this famous quote from Dizzy Dean, "Can't hit a curveball, shucks, get behind me, get behind a ball can't curve. Shucks, get behind a tree and I'll hit you with an optical illusion." Turns out physicists knew why balls were curving way before then. There was a physicist named Lyman Briggs who in 1917 actually put together a wind tunnel, which is something that introduces little streams of air with little smoke streams that allow you to see what the airflow around an object like a wing would be, and had pitchers throw curveballs into those streams. So this is actually a photo from one of Lyman Briggs' experiments. So even back in the early 20th century, physicists were starting to study baseball. So let me just give you a little background here. The key ingredient in how a ball flies from the pitcher to the plate is embodied in a subfield called fluid dynamics. And air is a fluid, and so a ball moving through a fluid would be fluid dynamics. Now, there are three regimes that we talk about when we talk about fluid dynamics. This is a photograph I took of a column of smoke from incense rising, and this is in my basement. Just like to burn incense in my basement for no good reason, and take photographs of it. So there are three regimes, one which is easily solved and one which is almost impossible to solve, but we know something about. There's a regime called the laminar regime, and this is where the molecules of air are forming a well-defined path, and it's always going to take the same path no matter what. So you could drop a molecule in here and always follow the same path. And then there's some transitional region where it starts to wiggle, and then it becomes chaotic and starts to do curlicues and make little tornadoes behind the baseball, for example, and it's hard to predict, although there are some regularities associated with the turbulence. So these are the three regimes, and the baseball will actually live live partly in a laminar regime and partly in a turbulent regime. And it's important to note that, as I said, a full mathematical and even computer simulations for fluid flow around baseball is still elusive. So we have to deal in approximations, and yet humans have figured out how to pitch baseballs and make airplanes fly. So I'm not going to try to make you know about all these principles that I'm going to bring before you. But here's a pipe that has water flowing through it or air flowing through it. And you see it's rather wide here, and the fluid flow is rather low. And then I constrict it, and I force the fluid to move much more rapidly. And what happens, as you see in the constrictions, is these streamlines, which trace out the path of molecules on a regular basis, get pushed together. And when they get pushed together and they're dense, they are moving at a much higher velocity. And then as it opens up and necks out again, it's at a much lower velocity. Now, if you were to sample the pressure in this region and the pressure in this region where it gets necked down, so it turns out when the airflow is really fast, you get low pressure. And when the airflow is really low, you get high pressure. So if I were to put a little meter or a little gauge between these two, you would see high pressure on this side and low pressure on that side. And in fact, I can illustrate that with a little demonstration. Physicists we're fond of demonstrations of one kind or another. So what I have here is a fan, which is going to blow air, and I have a little model of a baseball, I suppose. And this is kind of a cute demonstration that I used to see in Sears, right next to the vacuum cleaner department. So here we go. That actually illustrates this Bernoulli principle. I'll explain why. The exhaust of this thing is going to produce a very high velocity of air right at the center, and it's going to drop off as it goes towards the outside of the cone. So here you have high velocity, which means that you would have low pressure, and here you have low velocity, which means you have high pressure. Okay, what that means is that if you put the ball in here, if it kind of makes a little excursion down, it's going to feel the high pressure and gets pushed back. Or if it makes a little excursion up, it's going to feel higher pressure and gets pushed down. So there's like a little well, if you like, of pressure that is forcing that ball to sort of stay in that little pocket. And that's an example of Bernoulli's principle at work. It's how an airplane wing also works. If I draw a shape of a wing, something like this, what happens is the air gets forced above the wing and down, and these lines get pushed close together, and on the bottom they're much more lazy and they look something like that. So you see the lines are closer together here, faster velocity, lower pressure, they're farther apart, lower velocity, higher pressure, and you get a net lift that's pushing the thing up. Now, you've probably heard for every action there's an equal and opposite reaction. So what's happening is this airflow getting pushed down is that reaction, which is the action that's pushing the wing up. So that's how a wing works. That's how that ball works. Now, the next ingredient is what's happening at the surface of the baseball. If you have the baseball traveling along and you picture a little streamline, if everything was in this streamline regime, this laminar regime, you can imagine this molecule that's sort of going along and it has to make some decision. Do I go up or do I go down? And that line where it makes the decision is called a stagnation line. Now, right at the surface of the ball, what happens is the air will adhere to the surface because there's always a little bit of roughness, and there's a characteristic of airflow called viscosity, and you probably know viscosity when you think about maple syrup being very viscous and water being less viscous and so on. That viscosity causes the air to stick to the surface of the ball as it moves along, and as you go further and further away from the surface, it starts to gain some speed until you're at the ambient airspeed around it. And this little region here is called a boundary boundary layer, and that boundary layer is very important for how the whole aerodynamics of the ball gets set up. For example, if it's spinning, it's going to carry air around it. And in fact, the size of the boundary layer depends to some extent on the roughness of the ball. So the seams are going to play a role in the size of the boundary layer and how much air it carries around. If you scuff the ball, if you put a little bit of tar on the ball or something like that, it's going to tend to increase the boundary layer and suck more air around. And that's why umpires try to be rather scrupulous about inspecting the ball, and why pitchers are always trying to like carry some doodad that's going to scuff it up. So there's a little cat and mouse game going on. Now what happens in a baseball, when you give it spin, there's something called the Magnus effect. And as the ball spins, it carries air around through this boundary layer, and it pulls these streamlines together in the direction of the spin. So you see in this top region here, where it's spinning, the velocity of the ball is combining with the air that's getting pushed around to create a higher velocity up here and a lower one down here. So that net pushing of the streamlines together gives you higher speed, lower pressure, higher pressures down here, and you get lift. And this is called the Magnus effect. Now, I can demonstrate the Magnus effect with another little demo here. This is I don't know what the name of this apparatus here. This is called a trackball. And what I will do is I'm going to throw this out in the room, and it's going to spin off of this thing. I'm trying to make it into a curveball. So when it leaves this thing, it's going to be spinning this way. So that means that the air on that side is going to be at a higher velocity or a lower pressure, right? So if I'm going to start throwing it that way, I think it's going to curve that way. Now we'll see if I do well. So you guys don't mind a little styrofoam thing up there, do you? Okay. Okay, so I'm going to try to aim over there. Okay? You see that? So I threw it over there, but it curved the other way, and that was because of the Magnus effect at work. So now, and so I could get a top spin or down spin, but time is short, and you'd believe me. So depending on how the thing is spinning, okay, you can get it to go up, right? If it's spinning this way, I can get it to go down. If it's spinning that way, if it's spinning that way, it's going to go that way, sideways, and then you can have all sorts of combinations in between to control the flight of the ball. Now, this is an idealization of the flight of a ball. What really happens is you have this laminar flow in the front of the ball, but because the ball is moving so rapidly, I mean, typically pitchers will throw in the majors anywhere between, the slowest would be a knuckler around 65 miles an hour, up to about 98 plus miles an hour in a fastball. And what it leaves is a turbulent wake behind it of this kind of mush of air that's circulating around one way or another. And that can have an effect on baseballs as they move through the air. In fact, there's one very interesting effect which I'm going to try to draw your attention to. It's called the von Karman Street, the von Karman vortex street. And I have a little animation that I'm going to punch up in just a second. But this is very common to what happens if you hear the wind going through wires on telephone poles at very high speeds. They start to kind of make a whistling noise. Or if you are out on a sailing vessel and the winds are getting really high, you'll get this very scary kind of whistling noise that's happening. And what happens is the wind will form little mini tornadoes behind the wires, and those mini tornadoes will be regular, and if it just starts to excite the wire at the right speed, it'll start to sing along. So this was discovered, or the principle was elucidated by this guy Theodor von Karman, who was a Hungarian aerodynamicist and actually developed the theory of swept wing airplanes. So here's a little animation that shows the development of the vortices behind the. Oh, what happened there? I didn't want to do that. Let's see. Oh no, I don't want to do that. Previous. Okay. How do I? There we go. Now, if I push the button, how do I push the button? There we go. Yeah. Just give it a sec. There we go. Okay. So there you can see the von Karman Street effect behind a cylinder. okay, that waving thing, and it's rather regular in motion. And in fact, if you go back to Lyman Briggs' photo and you look at it carefully, you'll see all the elements that go into the fluid dynamics of a pitch and a curveball. So this is curving along that way. You see that the lines, the streamlines, are getting pushed closer together, which means that the ball wants to go up in terms of that slide. This, the physical picture. And then you can see the air overall is getting forced down, so that's the kind of the reaction force of the air that's giving you the action force of the ball going up. You can see the turbulence in the wake, and then you can see the little development of these von Karman Street tornadoes trailing behind the ball, which is going to push the ball around just a little bit, and is the basis to some extent of the knuckleball. So I can't talk about all of the details in great glory. So what are the effects on a pitch? There's gravity, which pulls it down. There is drag, which slows it down. So that can come in the form of friction of the air on the surface of the ball, turbulence behind it. Then there's spin. And the spin has two distinct effects. One is the Magnus effect, which I explained to you earlier, which gives it lift. And the other one is a kind of stabilization. So if I spin this thing, it's going to want to basically stay in one place and not get pushed around or destabilized. So the spin will actually try to keep it with its axis of rotation always pointed in the same direction. So that's why a lot of spin can help stabilize a ball, or the lack of spin can destabilize a ball. So in fact, the turbulence randomizes the motion. So if you throw a ball with little spin, but with this von Karman Street tornadoes forming behind it, you'll get a knuckleball. Okay, so here are some examples of balls that get thrown. There is your classic fastball, and when it gets delivered, it's getting spin, which is going to tend to give it some lift. So both the fastball will fall without spin, and with spin it will also fall, but not as fast. And typically fastballs are thrown around 90 miles an hour. It has this backspin of about 1,600 revolutions per minute, and it has about 12 revolutions between the time it leaves the pitcher's hand and reaches the plate. And this is just the ratio of the Magnus to the regular weight from gravity. Then there is the split finger fastball, which is thrown with the fingers, as the name might imply, split wide apart, tends to go at a slightly slower velocity, but it makes roughly the same number of revolutions between the pitcher's hand and the plate. But they try to impart a different kind of spin. Now, it's not necessarily a spin which is going in the opposite direction, so it dives down. But oftentimes, good split finger fastball pitchers will tend to give it a little bit of a side spin or an up-down spin associated with it. So, for example, this is a slow motion of Freddie Garcia's splitter, and if you look carefully, you can actually see that there's kind of an up-down sideways rotation, kind of at about sort of 2 o'clock to 8 o'clock or so rotation, and then you'll see it have a fairly straight path, but as it starts to lose velocity, the spin is going to give it a kind of fancy behavior right at the end. So let's take a look at it. It takes just a second to go. Okay, here we go. So there you see it spinning. Seems to be going straight, and just before the plate, wow, look at that. Yeah, okay. So that's a real master at work who's obviously solved the Navier-Stokes equations. There's the curveball, which is well known. I won't belabor it because you're trying to get sideways revolutions, and it's basically going to curve to one side. You throw it more slowly, so rather than getting 12 revolutions between the time that it leaves the pitcher's hand and the plate, you get up to about 17, and a fairly strong deflection. And here are a couple of examples of the difference between a ball with spin and without spin, and here is the vertical position of the ball in feet versus the distance from the pitcher. The blue would be with spin for a fastball, and the red would be without spin. And here is a curveball, and what would happen if you throw it straight, and you get a deflection of about 1.5 feet between the mound and the plate from that. Slider is just kind of a sideways, kind of a, I don't know, a hybrid, if you like, between a curveball and a fastball with a kind of a diagonal rotation coming into play. And then you get the famous knuckleball. And here you have a famous pitcher throwing a knuckleball with, originally back in the day, in the early 20th century, it actually was released from the knuckles of a pitcher, but there have been refinements since where the grip is the thumb and just one finger with, at least the case of this gentleman, very sharp fingernail. So there's only 2 points of contact at a reasonably high velocity, but the aim is to get no revolutions. And I'll talk a little bit about another biomechanics aspect of how this pitch works in a second. But the idea is that because there are no revolutions to stabilize it, those von Karman Street tornadoes are going to start to make the thing wobble around in a very unpredictable way, which is why it's so hard to hit. So let me talk for just half a second about the delivery, and I'm sorry to give you an equation you'll have to absorb, but here's a bullwhip, and the idea behind a bullwhip is the following. Conservation of energy. It is the product of mass times velocity squared. And if you look at a bullwhip, there's a lot of mass right at the beginning of the bullwhip, but it tapers down and gets narrower and narrower, narrower and narrower and narrower. So the technique, and I'm not going to crack it for you, could do it outside, I guess, later on, but I wanted to. I was actually scouting the room out, and I decided against it. So it has a lot of mass down here, and the person who's cracking it puts a kink in it. And what happens with that kink is that you have high mass, low velocity, but then as the mass gets lower and lower, the velocity increases because of conservation of energy until you get to the very end. And the very end of a bullwhip, I don't know if you can see it, but it necks down to just a set of threads. And so what happens is the end of the bullwhip, actually, although you're moving it at maybe 10 miles an hour at the start, it ends up going supersonic at the very end. And that's what the crack is the speed, the sound barrier is actually getting broken by the end of the bullwhip. Now, why on earth am I mentioning this to you? What does this have to do possibly with baseball? It has to do with the delivery. If you want to throw a fastball, okay, if you're just going to stand there and do this, you aren't going to get much out of it, right? So this is why pitchers have a big windup. The biomechanics of a pitch is just like how a whip cracks. You want to get a lot of speed out of that ball. So you have all this mass, and at least I do, all this mass and power in your core muscles, in your glutes, in your thighs, in your quads, and your abdomen, and all that. And so you have all this twisting motion that you can use and bring to bear that has a lot of mass and a lot of power. And what happens is you're throwing that kink. You actually develop a bodily kink, and that bodily kink, like on a bullwhip, travels down until you get to this very narrow part and finally the ball. And so in the same way as you're taking relatively slow velocity and high mass, what you're going to get is a low mass and a high velocity, which gives you a nice fastball. So one example, an extreme example, is Tim Lincecum, who is 5'11", and weighs 170 pounds. And for some reason, people say he has a very unorthodox delivery, yet it's just a very exaggerated delivery that's very whip-like in its in the way it looks. So let me just show this slow motion, and you'll see this whip-like motion that he's getting in this very extreme body rotation too. Takes a second. This is amazing. He puts his, he does a 360 turn in his pitch. Unbelievable. Okay, so you see how that looks like a whip uncoiling when he throws it. The other thing I should mention is his plant foot. On average, the plant foot for most major league players goes out about 5 feet. His goes out about 7 feet. And when he jams his foot down, what that's doing is that's taking and releasing all that bodily energy, all that bodily mass times velocity squared, and giving it a big boost. So just look one more time at this and see if you can see this sort of moment when his foot hits the ground, when all of a sudden everything is released at that point. So he sort of coils up, and when the foot hits the ground, boom. I mean, you see the hands are blur at that point. Okay, so just one more thing. This is the same throwing as throwing as throwing. If you kick a soccer ball, you have to do something very similar by winding up. It's also true in a javelin throw, and I'm going to show you this in a second, but I wanted to make a point. Throwing a javelin and throwing a baseball can be rather different. I actually had to coach some javelin throwers, my son's track team. And in fact, the coaches asked me to help them out, and they said, you know, why don't you coach javelin? And I thought they were trying to get rid of me, and I said, I don't know anything about javelin. They said, well, you're a physicist, you can figure it out. So the first thing I saw when the kids were trying to throw the javelin was that they were doing this, you know, and the thing maybe got 3 feet and just dived into the ground. Well, why was that? Because they were used to throwing a baseball. So what a javelin thrower has to do, they have to not only do this whip thing with the plant of the foot, but they have to get that thing tracking straight, because if they don't get it tracking straight, it's going to start to spin and dive into the ground. So I had to spend the better part of 2 weeks getting them to do this with the javelin to get it thrown straight. So it's a slightly different technique than throwing a fastball, but I'll show it to you, and you should at least get some sense of the tracking. It takes a second to wind up. Okay, so you see how that tracks straight as he's releasing that. At least I hope you did. Okay, so that brings us to the knuckleball. When you throw a fastball, when you do this thing, it's almost impossible to not get spin on the ball. I mean, your whole body is kind of having this motion where it's not tracking. If you want to throw a proper knuckleball, you don't want any spin, so you have to have a delivery that's much like the delivery for a javelin, except instead of going up, it's going more or less horizontally. So when you see the delivery of a knuckleball, you get a little bit of upward motion, but as it's leaving the hand of the pitcher, it's going to be going straight, so you don't get any rotation at all. So here's a Tim Wakefield knuckler. Just take a second and you'll see what I'm talking about in the delivery. Okay, you see that it's nowhere near that exaggerated overhand motion. And of course it's a strike. Okay, anyway, so that's enough from me, so I hope that you got some sense of the physics of how the ball flies. So thank you.
I want to thank everyone for coming and thank our panelists. It is a proper way to end a baseball game, and this is it. So again, thank you all for coming. I want to thank the panelists, and Jill, Robin, Mike, Steve, Andy, and John. You now know everything you need to know about throwing a pitch and the baseball card and everything else you need to know. And Hannes Wagner might be the best shortstop ever, but Derek Jeter has an argument to be made. Thank you, everyone. Have a good night.